Good to see you folks again. Happy to be back, at least physically. I got home about 2 a.m. this morning due to a late flight, and I'm feeling a little bit under the weather because of it, but it's all in a day's work. So I regret not being with you on Thursday, but I did ask you to watch the video as per email. I'm glad the message is delivered in such a colorful form. So, what was that video about that I asked you to watch? About what was the focus of that video? Sorry? Types. Typing. Not in a keyboarding sense, but in the sense of having a set of abstractions and, in fact, having a hierarchy of contracts associated with types. So we have subtyping and supertyping. And there's an important principle introduced that carries the name of one of the two definers of that principle. What was that principle? Liskov substitution principle. And what is that principle fundamentally about? What's sort of the basic focus of that principle? What does it concern itself with? Okay, so it comes up in a big way in inheritance, to be sure, but it's related to inheritance. Let's put it this way. But that's because inheritance often comes along with subtyping. As we'll see, issues of inheritance and subclassing have their own texture, and that goes beyond subtyping. Subclassing is about reuse of implementation. Subtyping is a relationship between contracts, between the promises made by types. What does the Liskov substitution principle focus on? What does it try to address? What does it try to provide? Yeah. Okay, so I'll refine that a bit, but you've got the essence of it. It's a principle that lays out rules for safe means of using subtyping, which typically goes along in an object-oriented context with subclassing, but you can actually have subtyping without subclassing. What's an example, and I know this is going to be confusing, but what's an example within languages like Java, Scala, C#, Objective-C, I believe as well, Swift. What's an example of how you can get subtyping without subclassing?
Interfaces?
Yeah, you have interfaces. You say that this interface, for example, is based on this other one, right? So it's not a full implementation. It's basically saying this interface, like a set interface, also it captures the same promises that are made in the collections interface, but extends them in a certain way. It extends them. And we can say, in fact, in Java that this class, moreover, implements these 5 interfaces, right? You could say it implements serializable. It implements serial numbered. That's really adverse. It implements iterable. And those would be examples of interfaces that are supported by the class. It turns out that in Java, and those other languages I've mentioned, we can have subclassing without subtyping. Subtyping without subclassing. But subclassing always comes along with subtyping. So this issue of safety and subtyping, which is what the Liskov substitution principle provides for, which is what it seeks to provide as a rule for what it means for something to be a behavioral subtype. Not just a nominal subtype, not just a subtype where we say, A implements B, and that's all the compiler knows, but one that, honest to goodness, it really implements B. It genuinely implements B. It's consistent with B. It is compatible with B. The place that this really becomes important is in the context of polymorphism. What is polymorphism?
Using subclasses for superclasses.
Yeah, or technically it's subtypes for supertypes. So I can have a class foo here, and a method foo. I could have one class that's a one type that's a subtype of another. So this could be set, and this is iterable or something like that. Those would be interfaces, or A could be a class, and it's a subclass of B. That's another subtype relationship. Carries subtyping as well as inheritance. But the point is that if A is a subtype of B, foo, the method foo, could take in a B. Take in a B and operate on that B, knowing purely that it's a B, whereas secretly, elsewhere in our program, far off over here, we have bar, which calls foo with something that's in fact a what? An A. Secretly, it's an A, right? Somewhere else in our program, we call foo with something that's not just any old B, it actually is an A, right? This is an example of polymorphism. We're passing around this A as if it's a B. That's why we say it's polymorphic. It appears in different forms. So this object, this A object that we allocate over here when we call foo from bar, that A object can appear sometimes as if it's an A, but sometimes it appears as if it's a B. It's treated as if it's a B. Its apparent type is a B, we use the term, and we distinguish that from its actual type, its underlying type. The true type of it under the surface is an A. It's really an A, but it can be passed around like a B. And in fact, there could be a whole type hierarchy up here, right? Doesn't even have to be linear. We could have C, D, E, right? These could be different interfaces. Iterable, serializable, serial numberable, and these could be different interfaces. We could pass A around as any of those, right? People comfortable with that idea? That's the idea of polymorphism. Why is that an advantage to be able to do that? Why does that offer us a lot of advantages? Why do we like polymorphism?
Type parameterization is more powerful.
Type parameterization is more powerful, so it allows us flexibility of types. I heard something else too, so that's true.
I'm still thinking.
Sorry? Yeah, okay. So why else might this be favorable?
Code reuse.
Code reuse. We could reuse. We don't have to rewrite foo for each of B, or each of A, E, C, and D, like a specialized version of it. It goes to what Connor was saying in a way, but we can reuse the same code. It's you can think of it as kind of a form of type parameterization. Yeah.
To contrast, you can also make a general function very different for multiple different types. So you can have each function overwrite the superclasses.
Yeah, that's true. You'd have the flexibility of having a different version if you wanted to for each of these, or you could make use of one here that actually I should be careful here because I said something that was possibly incorrect depending how I expressed it. I should be careful here. Could we pass? So we can pass around an A to foo as if it's a B, right? Can we pass around a D as if it's a B? No. Can we pass around a B as if it's a D? Yeah, and that's what I was trying to get at. That A could be passed around as if it's a D, as if it's a C, as if it's an E in different circumstances. and we could in principle have different parts of our program that they're relying on D's, E's, C's for different purposes. Some iterate over them, so they need an iterable, and etc. Some serialize, some put things out, they marshal them and send them off to another machine, or they put them, they call off to a process on the same machine but in a different memory space, and they have to be serializable. They stick it in a database and it has to be serializable. So sometimes we could treat A as a serializable thing for some code. Other cases it's treated as a B, etc. So polymorphism gives us big advantages, but what does this have to do with Liskov's substitution principle? Why is the fact that we can use polymorphism in our programs, in our object-oriented programs, a big motivation for the Liskov substitution principle? Because we want to be able to do this my habits.
Is it sanely?
Sanely?
Safely.
Okay, I'll accept sanely.
Safely.
Safely is what I had in mind, but I'll accept sanely. Because you could be driven bonkers by bugs if you do not adhere to this principle. You could be driven bonkers by it. So I'll say safely, but I'll put an N there. Okay, and then it becomes a crossword puzzle. Sanely as well. We want sanity, we want safety in polymorphism. We want some criteria that says, okay, if A is being passed around as a B, what are the rules for how A has to be defined for this to be safe? For it to be treated as a B, A can't just do anything in the world. It turns out. It doesn't have, it has a certain amount of freedom. It actually has a lot of freedom. But there's certain things it's got to do for it to be treated legitimately as a B. If B has a square root, SQRT routine, right? If B has a square root routine, and people are counting on from the specification this to take a square root within a certain tolerance, and then A overrides square root, its own square root, and it actually totally ignores the tolerance, or it performs the cube root, or it always returns 1.0, then A is nominally a subtype of B here. Maybe it implements B, or it extends B in Java. It's nominally a subtype of this. It can be passed around, because the compiler knows it can be passed around like a B. But it's not behaviorally a subtype. This is not consistent with the definition of what we expect for the promise. It does not adhere to these promises of B. So for A to be passed around as a B, not only does the compiler have to be able to accept it, which we get by saying A extends B or A implements B or what have you. That's just sort of the crude nominal sort of criteria. Really, A needs to be consistent with B in some deeper sense. And that, ladies and gentlemen, is what Barbara Liskov and Jeanette Wing identified as sort of the core principles to identified to address that need. Okay. Now, what I'm going to do, because it looks like there's a mismatch between the screen and what's on my screen and what's on the projector,